Hello everyone, welcome back to the 5 Minute Tech channel. Today we'll be talking about how to build your own local LLM. I'll talk about the topic involving the building a local LLM completely from scratch on a standard CPU. There are different steps which are involved, so let's get started. So first of all, to build an LLM, we need to understand what we understand by LLM. An LLM at its core is a data transformation pipeline, and in basic sense it consists of two parts, which is a Python script that defines the mathematical structure and a uh, massive binary file of decimal numbers called weights. When we prompt our LLM, we just are pushing our text through those static numbers to calculate the highest probability of what the next word should be. And then it is, as we talked about, there are two parts to it: a Python script, which is the plumbing area, which you can see on the left hand side, and the weight file, that is the state, which has the billions of decimal parameters, static numerical data. So what is the anatomy of a parameter? You input x and you get output y. You have the weights multiplied by your input data, and then you add some biases if there are any. So weights basically are the strength of the connection. It determines how the influence of an input has on the output, like a volume dial on a specific instrument. And similarly, the bias will be a threshold for activation. It allows the model to shift the output up or down regardless of the input, like the master volume floor. So this basically is the parameter anatomy. Now, linear transformation, we just talked about y is equal to wx plus b, where w being the weight and b being the bias, whereas x and y being the input and the output respectively. The conceptual and historical root comes from the fact that the volume dial metaphor, the input are scaled by learning the dials, that is the weights. Then there is a mathematical bedrock, which we talked about, the linear transformation. The y being your output and w being your weight. The results resulting in the numbers passed to the next layer. Weights being your matrix of learned dials, scales input importance. So massive grid of dials will be present, that is determined, that is called as weights. The x input, with the data flowing in, example your embedded token, and your bias will be the extra learned number of shift results, the baseline trigger. The linear method applies a linear transformation to the incoming data. It is similar to the linear transformation, and we'll be talking more about it when I walk you through the code which implements a local LLM. The learning loop, how random numbers become language. So you can think of it as like I input text being something like the cat sat on the, and the fill in the blanks, and then there are random dials and the output guess probably maybe like a xylophone, which will be a high loss because that's not appropriate, that will not fit in the sequence of words which we have already provided. So there will be back propagation, we will adjusting the dials, and the input again, when it comes like the cat sat on the dash, the output guess being mad will be a low loss or a high accuracy. So forward pass, the model takes an input and runs it through the random dials to guess the next word. Now calculating loss, it calculates the loss while the training happens. We compare the guess to the truth, and the math calculates a loss score, which I will be showing you in the demo, by the way, exactly how far the model missed the target. And then there is a back propagation where the optimizer nudges the every dial of the network. Dials that cause the wrong guesses are turned down, and dials that led to mad are turned up. Now this intelligence is not programmed, it is a statistical result of billions of micro adjustment that happens. Now in the evolution and parameters, how it evolved, this LLM space. So to understand how we got here, we have to look back at 2017. Before then, the models read text sequentially, word by word, which was slow and lost context over long paragraphs. And then there was a Google research which was published as a paper called "Attention is All You Need," which introduced something called as transformer. Now it allowed models to look at all the words simultaneously. Since then, the architecture hasn't changed drastically. We just scaled up the parameters, and we have the parameter is just one of those decimal numbers in our weight file. And our model today is having will have a few thousand of them, whereas GPT-4 has over like a trillion. So building the pipeline from scratch, what are the architectural layers? First is tokenizer, which is word to token breakdown, followed by embeddings, that is the clean embedding of embedding graphs with vectors. Then we have transformer blocks, wherein we stack transformer blocks, which includes your feed forward network and context processing network, followed by a probability output. Now there is some loss calculation which happens using calculus, weight based weight adjustment. So first point, what was the tokenization in embeddings? Step 1 is our input, wherein the neural network cannot process string, then they only process matrices of numbers, as we talked about. Our tokenizer creates a dictionary, assigns a unique integer to every character or word. We then map that integer to an embedding, a high dimensional vector, and this allows the model to map semantic meaning mathematically. Words with similar meanings end up closer together in the mathematical space. The step 2 is your engine, which is the self-attention. Step 2 is the core of your transformer, that is when our model reads a word like bank, it doesn't know if it is a river bank or a financial bank. So every token generates three vectors: a query, what am I looking for, a key, what do I contain, and the value, that is my actual data. The model multiplies the queries and keys of all the words in a sentence together to find the contextual relationships, mathematically routing the right context to the right word, and that's how the linkage happens. Step 3 and step 4 are the forward pass and the back propagation, in which the step 3 being your forward pass, data flows forward, network guesses the next word, and so forth. Whereas back propagation is the loss functions and update. It gives up percentage, the loss number, how much loss is happening, and accordingly adjusts the response again iteratively. So we'll move now to the demo. Okay, to start with, we'll open Windows PowerShell in the folder of our choice, and we'll go ahead and make a directory, followed by cding into it. So that is done. Now we will go ahead and do if you don't have UV package, you can install it in your system, else you can go ahead and run the UV in it. But if you really want to have the UV first, you may need to install the UV plugin, UV through this command line, wherein you download and install it into your Windows. I'm running in Windows, so I'm giving you the command for the Windows. Now we'll go ahead and do initialization, as I have already installed UV in my system. So that is saying it is initialized our project. We'll go ahead and open the project location in our Visual Code. So I've just launched my Visual Code here. I'll go ahead and add the first file, which is okay. Before that, we have to install the a dependency, which is our PyTorch, which will be our main dependency here. So let me install the PyTorch. PyTorch has installed now. We'll go ahead and add the code in our Visual Studio now. We'll go ahead and update our project toml file, and we'll go ahead and create our data text file. So let's create a data text file here. Content of data text file to begin with will be a simple sentence about what is machine learning, and the next one is our model.py file. We'll create a model.py file here. So let's go ahead and create model.py, and I'll put in the code, and then we will talk about the code. So the first part of this code is we get the dependencies in terms of PyTorch, and then what we do is we do hyperparameters, keeping this small, so it runs instantly on our CPU system. If you have GPU, you can scale it up. We'll run on a batch size of 32, block size of 8. and we will be playing with the max iterations. We'll start with 1000, we can change it to 5000, 50,000, and 500,000, which I'll be showing you subsequently, along with learning rate, the n embed, and the device, which is our CPU. Then we will have the three areas: the tokenizer, the batch generator, and the basic transformer which we have in our system. And then we have the training loop, wherein we call the method the tiny language model, and create the pass the value to the optimizer, and then we run the loop. So this is the pretty simple code which will not only create the language model, but also create pass a particular input, as you can see, and generate an output and show us on what is happening there. So after completion of the training, it will generate the new text based on the learning pattern, and then it will generate the output of whatever is coming out of the LLM. Now let's go ahead and run this model. So we will go ahead and do uv run model.py. So uv run model.py. Now it starts running the model file which we have. So it is saying that the numpy, no module name numpy, so we need to go ahead and install the numpy now. We'll just do is uv add numpy, enter. And then rerun our model. And as you see, we were talking about the loss part. So how much is the loss, and number of steps which is run, and then on the basis of the text, if you see, it is completely inaccurate and gibberish text which is coming across to us. Now we'll go ahead and do one thing. We'll go ahead and change the number of iterations that we do. So we'll go ahead and make this as 500,000 and save this and rerun our PowerShell. We'll go ahead and rerun the model. So this will continue to run for some time, and it will try to train our model, and you can see the number, the loss will repeatedly reduce over period of time. So as you see, now it is into 0.9, and subsequently it will enter into 7, 6, and so forth. As you see, now the loss is around 0.8, most of the time 0.7 as well, and it is reducing by the number of iterations. Now we are into 79,000 iterations, and it is mostly now 0.8 ish, around along with some 0.7 ish numbers. And as we are nearing 500,000, you can see it is around to 0.7, 0.8, which will keep reducing till we reach around 500,000 iterations. So now we are nearing 500,000 iterations, and we will be seeing the result now. It is close, loss is around 0.7 ish most of the time. Sometimes it is 0.8 as well. So we'll be getting the result now. And you see the result is that some of the words are formed properly with next, and then there is also from, the so it, next. So it is trying to form the words, but still it is not 100% accurate. there would be much more iterations required to make it work better. So in that case, we'll be changing our implementation a bit to make the word level prediction look good. We need few paragraphs of coherent text so that it has enough words to shuffle around. So we'll go ahead and make some changes in the data.txt file. Our current data.txt file is pretty small. We'll go ahead and augment this with more text around the machine learning, and also what we will do is we'll change our model.py code base to this, wherein what we are doing now is we are keeping the we're going to do a now 8 word of context, not 8 letters. So that is a major change. And here also we will be doing around 1000 first, and we'll see the result and then take it from there. So we'll go ahead and run the model again now. So we'll go ahead and run the model. So when we're entering the machine, it is coming as machine learning is a CPU. We keep the architecture small and efficient by looking at the context of previous word, the language processing by look at it. So even though it is not very accurate, it is still able to form the words together and make a sentence. Now let's go ahead and increase it to a higher number. So I'll go ahead and increase this to around 50,000 or maybe 100,000, and you would be able to see the difference. So now we have run it 100,000 times, and if you see now the prompt machine, the output is coming as machine learning is a fascinating field of artificial intelligence. We are building a neural network from scratch using Python and PyTorch instead of reading individual letters. So it is coming pretty accurate now, and this is how we have built today, and exactly how Llama, Gemini and GPT-4 work. The only difference is scale. Instead of few paragraphs of text they read the entire internet, and instead of one CPU they use clusters of 100,000 or 10,000 GPUs. I would highly encourage you to check out the Andrej Karpathy's Nano GPT repository and his Zero to Hero video series, which heavily inspired this implementation and is the standard for learning this architecture deeply. I hope you like this video. If you like the video, press like and subscribe to the channel. Have a nice one.